In this video, I'm going to be talking about rates of change. And this is a really good application day of all of the work that we've been doing thus far with derivatives. Okay, average versus instantaneous rate of change. Remember, average is the slope of a line. So say I have a function on an interval from a to b. All this is the slope of a line. F of a minus f of b minus f of a all over b minus a. Versus instantaneous rate of change is just the derivative of that function. So one big application that we use this on constantly is particle motion. So the function s gives the position relative to the origin is called the position function. So we have a function s, typically written as s of t, and that is our position function. If over a period of time, delta t, the object changes position by a certain amount. So this is like subtracting two different positions. Then we have a familiar formula, distance equals rate times time, or distance over time equals rate. And we get that from distance equals rate times time, solving for a rate. So the average velocity is the change in position over the change in time. Remember, our change in position is this formula. So I'm basically subtracting two different position coordinates over my change in time. Remember, delta means change. So my average velocity, what this really is this is the slope of a secant line. Subtracting two position values over the change in time. Instantaneous velocity is the limit of that function, so the limit of that, which is the derivative of position. Okay, so said another way, s of t stands for my position function, s prime of t is my velocity function. The absolute velocity is called the speed of our particle. Think about a speedometer, okay? Speedometer just tells me how fast I'm going. Remember, velocity gives us direction and how fast I'm going. So looking down at this chart down here, if I have a positive velocity, I'm moving right or up. If I have a negative velocity, I'm moving left or down. A lot of times when we talk about particle motion, we're talking about something moving along, say, the x-axis. So if I'm moving right in relation to the origin, I'm moving that way. Moving left, I'm moving that way. Now, I could be over here in the negatives, moving towards the positives. That would also be considered going right. And the derivative of velocity, coming back over here, is our acceleration function. Okay, first example. A tennis ball is dropped from a height of 150 feet. The ball's height, s, at time t, is measured by that function, where s is measured in feet and t is measured in seconds. Find the average velocity. So here I'm looking for average velocity. So that is going to be the slope of the line through the two endpoints of that function. So doing the math, we have 86 minus 134 over 1. It simplifies to negative 48 feet per second. Find the instantaneous velocity. So the instantaneous velocity is the derivative of position. So I take the derivative of our position function to get negative 32t. And then I find v of 1.2, and that is equal to negative 38.4 feet per second. And my units, okay, velocity, remember, is a rate. So distance over time. average velocity. Okay, the units on top here were a distance rate. This was a time. That's how I got distance over time. Is there a time on the interval where the average velocity, so my average velocity, which is right here, equals the instantaneous velocity? Instantaneous velocity is that function there. So I set my instantaneous velocity function equal to the average velocity, and I get t to be 1.5 seconds. Okay, example 2. A diver jumps from a platform diving board that is 32 feet above the water. The initial velocity is 16 feet per second. Diver's position is given by that formula. I'm always going to give you the position formula. In physics, you have to build that position formula, but in calculus, we don't have to worry about building that formula. So, when does the diver hit the water? Well, my position above the ground, when I hit the water, is 0. Let me make that look a little bit more like a T. Pull out or factor out a negative 16. Carrying this up over here. Now I try and factor more. T equals 2 or negative 1. Now, we don't have a time machine, so we ignore the negative 1. Typically, I might put in here anytime t, where t is greater than or equal to 0. Okay, so just so you know that, I might do that. I usually have that written in there. I think it's in the next example. So when does the diver hit the water? T equals 2 seconds. I was looking for units. What is the diver's velocity upon impact? Okay. So the derivative of my position function is velocity, so that's negative 32t plus 16. I have to find v of 2, and we get negative 48 feet per second. Okay, example 3. And this one is more consistent with something that you might see on the AP exam, though they have been giving more and more real-life applications like we just saw. So a particle moves along the line, so its position at any time t is greater than 0, greater than or equal to 0, is given by that function, where s is measured in meters and t is measured in seconds. So that has some units for me. Find an equation for the velocity and the acceleration functions. Okay, so my velocity function is the derivative of position and my acceleration function is the derivative of velocity, which is 6t minus 18. Okay, when is the particle moving left? When is the particle moving right? Particle moves left when my velocity is less than 0. We move right when our velocity is greater than 0. So I have to take this velocity function and set it equal to 0. So I take that velocity function. I'm going to factor out a 3 since 3 goes into all of the terms. And then I factor, so I get t equals 4 and t equals 2. So let's now do a number line chart. Since t has to be greater than 0, 0 is a stopping point. And then I put 2 on there and I put 4 on there. And our particle continues forever. So what you do is you have to figure out what the sign of your velocity function is. So I plug in a number between 0 and 2. So if I plug in 1, I plug it into this velocity function here. If this was, say, set equal to v of t. And I figure out, am I positive or negative? If I plug in, say, 1 there, I get a negative times a negative, so that's a positive, so I'm moving right. Between 2 and 4, say I plug in 3, I have a negative times a positive, so that's a negative. I'm moving left. And something greater than 4, 5, I have a positive times a positive, so I'm moving right. So our final answer. We're moving right from 0 to 2. I include 0 because if I plug in 0 into my velocity function, I actually get a positive number out. We don't include 2 because technically that's where our velocity equals 0. And then from 4 to infinity. And then we move left on our interval from 2 to 4. Okay, what is the particles? So this is just a continuation. I just didn't have enough room to write everything on one slide. What is the particle's velocity when its acceleration is 0? So from the other slide, our acceleration formula is this. I set that acceleration formula equal to 0, and I get t equals 3. I now need to plug into my velocity function. I'm going to use the factored version because, quite honestly, it's a lot easier. And let's see what my units are. My units for acceleration, or I'm sorry, we're looking for velocity, are meters per second. Okay, this last one, this is a pretty hefty one, actually. What is the total distance traveled by the particle on the interval from 0 to 3? What is the displacement traveled? So let's deal with total distance first. And let's talk about what happens. So, total distance. Look at it like you're on a number line here. Okay? And I have to find S of 0. S of 0 is negative 8. So say 0 is here, I'm over here at negative 8. That's where my particle is starting. We know from this down here that I'm moving right from 0 to 2. So I'm moving right. I have to find what S of 2 is because that's my first time that I stop. S of 2 is 12. So I actually move right all the way to 12. Our particle. And then the next point I find is S of 3 since that's the end point. S of 3 is 10. So we know our particle turns around and heads back and is here at 10 at t equals 3. So you have to find the total distance, that's what I'm finding now, is S of 2 minus S of 0, so the length of this first segment, plus S of 3 minus S of 2, so that is equal to 12 minus a negative 8 plus S of 3 is 10 minus 12. So that whole thing equals I'm sorry, I was looking at my notes. I don't know why. That should be a plus in there. I think I should be doing absolute values because I'm looking for what's this total length. This total length is 2. So that should be 22 meters. Remember, total distance is like, I think about it as my Fitbit. How much have I put on my Fitbit during the day? This segment length essentially is 12. I'm sorry, it's 20, and then I add another 2 to it. So I think I should probably have some absolute value signs in there. I apologize. But I'm not going to lie, I've recorded this video 3 times today. This is the last time I'm recording it because I kept making mistakes. Now, when I'm looking for the displacement, all displacement is S of 3 minus S of 0. So where I start from where I end versus where I started from. So I have 10 minus a negative 8. So that is 18 meters. So I basically traveled in relation to where I started. I'm 18 meters away. But I went a total of 22 miles. Or 22 meters, I apologize. Okay? So that is my video on solving rates of change, or I typically call this particle motion.